Imagine standing outside on a clear night, far from any city, far from any light pollution, and tilting your head back to stare into the absolute darkness above you. The stars are there, thousands of them, scattered like salt thrown across black velvet, and somewhere beyond them, beyond everything you can see with your naked eye, there is a signal, a whisper, a faint, almost inaudible hum that fills the entire universe in every direction you could possibly point your finger. It doesn't come from one star. It doesn't come from one galaxy. It comes from everywhere. It is the oldest light in the universe, a relic of a moment so ancient that it predates every planet, every sun, every atom as we know it, and it has been traveling toward your eyes since the universe was just a few 100,000 years old. Scientists call it the cosmic microwave background radiation, and for decades, they believed it was almost perfectly uniform, almost perfectly smooth, a gentle and ancient whisper that told a story of a universe born in chaos that quickly settled into beautiful, symmetric order. Almost. Because then, tucked inside that ancient signal, hidden in data so vast and complex that it took the most powerful space telescopes ever built to decode it, scientists found something they were never supposed to find. A pattern, an alignment, a direction in the universe that seems to have a special quality, as if the cosmos itself has an axis, a preferred orientation, a kind of cosmic arrow pointing across billions of light years toward something no one can explain. And because the discovery was so unsettling, so deeply troubling to everything cosmologists thought they understood about the universe, one of the researchers who found it gave it a name that was simultaneously brilliant and terrifying. He called it the axis of evil, not because of politics, not because of any human conflict, but because if this axis is real, if this alignment is not a mistake or a statistical fluke, then it threatens to overturn some of the most fundamental principles of modern cosmology. Principles that took centuries of genius-level thinking to construct. Principles that form the bedrock of everything we think we know about how the universe began, how it evolved, and what it looks like on the grandest possible scale. And right now, in laboratories and observatories and conference rooms where the world's most brilliant minds gather to argue passionately about the nature of reality, the axis of evil remains one of the most hotly debated, deeply mysterious, and genuinely frightening anomalies in all of modern science. So let's go back. Let's go all the way back, farther than you've probably ever gone in your imagination, to a moment that is almost impossible to picture but absolutely essential to understand. Let's go back to a time before stars existed, before galaxies had formed, before any of the structure we see in the universe today had taken shape. Let's go back to just after the Big Bang. Picture this. The universe is roughly 380,000 years old. That sounds like a long time, and by human standards it is, but in cosmic terms it is nothing, an eye blink, a fraction of a moment in a story that has been unfolding for nearly 14 billion years. At this point in the universe's life, everything that will ever exist is packed into a space that is unimaginably hot and dense, so hot that atoms as we know them cannot even hold themselves together. The universe is a plasma, a swirling, glowing, opaque fog of protons and electrons and photons of light, all interacting so furiously with each other that nothing can move freely. Light itself is trapped. It bounces and scatters and cannot travel in a straight line because the universe is too dense, too hot, too chaotic. Then something happens. The universe expands. It cools. And at a temperature of about 3000 Kelvin, roughly 5,000 degrees Fahrenheit, something extraordinary occurs. The protons and electrons finally slow down enough to combine. They form hydrogen atoms for the first time. And in that moment, the universe becomes transparent. The light that had been trapped, that had been bouncing around in that opaque fog for hundreds of thousands of years, is suddenly released. It floods outward in all directions, filling the entire universe with a brilliant glow. In the language of physicists, this moment is called recombination, or sometimes the epoch of last scattering. And the light released in that moment, that ancient photon bath, is what we now call the cosmic microwave background. Ask yourself this question, right now, wherever you are listening to this. What would it mean if the oldest light in the universe, light that has been traveling for nearly 14 billion years, was not random. What would it mean if it carried a message? Not a message from an alien civilization, but a message written into the fabric of space and time itself. A message that seems to say the universe has a direction, a special axis, a kind of cosmic spine. That is exactly the question scientists found themselves asking when they first discovered the axis of evil. And the answer, or rather the terrifying lack of a clear answer, has been haunting cosmology ever since. To understand why this discovery was so shocking, you first have to understand what cosmologists expected to find. The standard model of cosmology, the one that has dominated scientific thinking for decades, is built on a principle called the cosmological principle. This principle makes two bold claims about the universe at the largest scales. First, it says the universe is homogeneous, meaning that matter and energy are distributed roughly the same way everywhere you look, that no region of the universe is special or different from any other. Second, it says the universe is isotropic, meaning that it looks the same in every direction, that no direction in the universe is preferred over any other. These are not small assumptions. These are the foundational pillars on which almost all of modern cosmology is built. The equations that describe the expansion of the universe, the models that predict how galaxies form, the calculations that tell us how old the universe is and what it's made of, all of these depend on the cosmological principle being true. If it is wrong, if the universe has preferred directions or preferred regions, then the entire edifice of modern cosmology is built on shaky ground. And the cosmic microwave background was supposed to be the ultimate proof that the cosmological principle was right. Because when you look at the CMB in its entirety, it really does look almost perfectly smooth. Its temperature is remarkably uniform across the sky, hovering at around 2.725 Kelvin, which is about negative 270 degrees Celsius, just a hair above absolute zero. The fluctuations in temperature from one spot to another are tiny, just 1 part in 100,000. That is a level of uniformity that staggers the mind. Imagine measuring the temperature of the entire surface of Earth and finding that it never varied by more than a fraction of a degree no matter where you looked. That is roughly what the CMB looks like at first glance. But first glances can be deceiving. When scientists began to analyze the CMB with increasingly powerful tools, they discovered that within those tiny fluctuations, there were patterns. And these patterns were supposed to be random. They were supposed to be the kind of random quantum fluctuations that were stretched to cosmic scales during a period of rapid expansion called inflation, a period that took place in the very first fraction of a second after the Big Bang, when the universe expanded exponentially fast. Inflation was supposed to have ironed out any special directions or preferred orientations, leaving the universe smooth and isotropic on the largest scales. That was the expectation. That was the prediction. That was the cosmological gospel according to the standard model. And then the data came in. The first major satellite dedicated to mapping the CMB in extraordinary detail was called COBE, the Cosmic Background Explorer. Launched by NASA in 1989, it gave scientists their first real full-sky map of the CMB, and it confirmed the basic picture, an almost perfectly smooth background with tiny temperature fluctuations. The scientists who led the COBE mission, George Smoot and John Mather, were eventually awarded the Nobel Prize in Physics in 2006 for this work. Their discovery was celebrated as one of the greatest achievements in the history of cosmology. But COBE had limited resolution. It could see the broad strokes of the CMB but not the fine details. So scientists built a more powerful successor. Launched in 2001, the Wilkinson Microwave Anisotropy Probe, known as WMAP, was designed to map the CMB with much higher precision, to measure those tiny temperature fluctuations in exquisite detail and compare them with the predictions of the standard model. When the first WMAP data was released in 2003, it confirmed many of the predictions of standard cosmology brilliantly. Scientists were thrilled. The universe appeared to be flat. It appeared to be about 13.7 billion years old. It appeared to be composed of roughly 73% dark energy, 23% dark matter, and just 4% ordinary matter. These were remarkable results, and they were celebrated around the world as a triumph of human scientific achievement. But buried within that data, there was something else. Something that the press releases didn't shout about. Something that made certain cosmologists go very quiet. When scientists looked at the largest scale fluctuations in the CMB map, the fluctuations that correspond to the biggest patterns in the universe, the ones that span billions of light years, they found something wrong. The quadrupole and octupole moments, which are measures of the largest angular patterns in the CMB, were not doing what the standard model said they should do. They were aligned with each other, and more strangely, they were aligned with the geometry of our own solar system, with the plane of the ecliptic, the plane in which the planets orbit the sun, and with the direction of the equinoxes. This was not supposed to happen. The universe, according to the cosmological principle, should have no idea that our solar system exists. It should have no special relationship with the geometry of Earth's orbit around the sun. The fact that the largest patterns in the CMB appeared to be aligned with the local geometry of our solar system was deeply, unsettlingly strange. And it was this alignment that cosmologist Kate Land and her colleague João Maguejo at Imperial College London named the axis of evil in their 2005 paper. The name was a deliberate provocation, a cheeky borrowing of political language to signal just how troubling and potentially paradigm-shattering this finding was. Because if this axis was real, if it wasn't just an artifact of measurement error or foreground contamination or some systematic glitch in the instrument, then it was evil in the cosmic sense. It was a threat to everything cosmologists held dear. Let's pause here for a moment and really let that sink in, because I think it's easy for this kind of scientific information to wash over you without fully hitting home. So let's make this personal. Right now, you are on a planet that orbits a star. That star and its planets exist in a particular orientation in space. The planets trace out a flat plane as they orbit the sun, and that plane has a specific orientation relative to the rest of the galaxy and the rest of the universe. Scientists have been telling us for a long time that this orientation is utterly meaningless on the cosmic scale, that the universe looks the same in every direction and doesn't care about us or our solar system or our galaxy. We are, in the grand scheme of things, nothing special. Just a tiny speck in a vast and indifferent cosmos. But what if the universe does care? What if the very fabric of space and time has some kind of preferred direction that, by some extraordinary coincidence, or by some even more extraordinary design, aligns with our own position in space? What does that say about our place in the cosmos? What does that say about the nature of reality? These are not idle philosophical musings. These are the actual questions that real scientists are wrestling with right now, in the 21st century, as they stare at CMB maps and argue about statistics and systematic errors and the nature of the universe. Now, before we go further, it's important to be clear about something. Science is not a collection of absolute truths delivered from on high. It is a process, a method, a way of testing ideas against evidence and refining our understanding over time. And the axis of evil is, above all else, a scientific controversy, one where serious, brilliant people disagree, sometimes quite passionately, about what the data means. So as we explore this topic, we are going to look at all sides. We are going to look at the evidence that suggests the axis of evil is real, and we are going to look at the arguments that it might not be. And we are going to ask the hard questions that neither side has fully answered. Let's start with the evidence. What exactly did scientists find, and why is it so disturbing? When cosmologists analyze the CMB, they use a mathematical tool called spherical harmonics to decompose the temperature map of the sky into components of different angular sizes. Think of it like decomposing a piece of music into its individual frequencies, its bass notes and treble notes. The very largest patterns in the CMB are called the dipole, the quadrupole, the octupole, and so on. Each of these represents temperature variations at a specific angular scale across the sky. The dipole is the largest pattern, and it is understood to be a local effect caused by the motion of our solar system through space. It's not considered a cosmological signal. But the quadrupole, which represents temperature variations at angular scales of about 90 degrees, and the octupole, which represents variations at about 60 degrees, are supposed to be genuine cosmological signals. They should reflect the real structure of the universe at the largest scales. And here is where things get strange. When WMAP measured the quadrupole, it found that the power in that component was significantly lower than the standard model of cosmology predicted. The quadrupole was weak, unexpectedly, mysteriously weak. And then, when scientists looked at the orientation of the quadrupole and octupole patterns, they found that these two components were aligned with each other far more closely than they should be by chance if the universe were truly isotropic. Think of it this way. If you threw two needles into the air randomly, the chances that they would land pointing in exactly the same direction are very small. That's roughly what the alignment of the quadrupole and octupole is like. The probability that this alignment occurred by chance, assuming the universe is isotropic, is estimated by various researchers to be somewhere between 1 in 1,000, 1 in 10,000. That's not impossible, but it's the kind of odds that makes a scientist sit up and take notice. That's the kind of coincidence that suggests something is going on. But the truly eerie part, the part that gives the axis of evil its name and its power, is the direction in which this alignment points. The quadrupole and octupole planes are both aligned roughly perpendicular to a direction in space that corresponds to the direction of the dipole anisotropy, which is related to the motion of the solar system. They are also aligned with the ecliptic plane, the plane of the solar system. And they point roughly toward the Virgo cluster, the nearest major cluster of galaxies to our own. Is that a coincidence? The universe has no reason to know where our solar system's ecliptic plane is. It has no reason to align its largest structures with local geometry. If the universe is truly isotropic, truly indifferent to any preferred direction, then this alignment should not exist. It should be as likely as finding two randomly tossed needles pointing in the same direction. So let's ask another question you can think about at home. If you were given a map of the entire universe, and the largest patterns on that map were all aligned in one direction, what would you conclude? Would you think it was random chance? Would you think the map was wrong? Or would you think the universe might have a secret it hasn't told us yet? The scientific community's response to the axis of evil was not unanimous. There were immediate skeptics, brilliant ones, who argued that the alignment might be an artifact rather than a real signal. And they had good reasons for their skepticism. One of the first things scientists suspected was that the alignment might be caused by foreground contamination. The CMB is not the only thing emitting microwave radiation. Our own galaxy, the Milky Way, is full of gas and dust that also emits microwaves, and this galactic signal can contaminate the CMB data if it is not properly subtracted out. When you map the CMB, you have to mask out the galactic plane where the contamination is worst, and how you do this masking can affect what you see in the remaining data. Could the axis of evil be a result of imperfect foreground subtraction? Could the alignment be caused by galactic microwave emission that scientists failed to remove? Some researchers argued yes. They built models of the galactic foreground and showed that, in certain scenarios, leftover contamination could produce an apparent alignment that looks like the axis of evil. But other researchers pushed back. They showed that even after applying different foreground subtraction methods, even after using different galactic masks and different analysis techniques, the alignment persisted. It was stubborn. It refused to go away. And that stubbornness is what makes it so interesting and so troubling. Another argument against the axis of evil is more philosophical, and it's called the look elsewhere effect, or in more technical language, the issue of a posteriori statistics. This is a subtle but important point. When scientists analyze complex data, they are looking at many different statistical measures simultaneously. If you look at enough different statistics, by chance alone, some of them will appear unusual, even extremely unusual. This is similar to the fact that if you flip a coin 1,000,000 times, you will inevitably get some long runs of heads or tails that look improbable in isolation but are perfectly expected given how many flips you made. So the question is, was the alignment of the quadrupole and octupole something that scientists predicted before looking at the data, Or was it something they noticed after the fact? If it was noticed after the fact, then the true probability of the alignment being a chance occurrence is actually higher than the naive statistical estimate, because you have to account for the fact that scientists were looking at many different possible anomalies simultaneously. This is a serious concern, and honest cosmologists acknowledge it. The axis of evil is not a prediction of any theory. It was discovered by looking at the data. So we have to be careful about overstating its statistical significance. But here is the counterargument, and it's a powerful one. The axis of evil has been confirmed by multiple independent analyses, using different methods, different data sets, and different statistical tests. It was seen in the WMAP data. It was then seen in the data from the European Space Agency's Planck satellite, which launched in 2009 and provided the most detailed map of the CMB ever made, with a resolution far superior to WMAP. The Planck collaboration published their CMB analysis in stages, and in their papers, they confirmed the existence of the large-scale anomalies, including the alignment of the quadrupole and octopole and the low power in the quadrupole. The Planck team noted, with characteristic scientific understatement, that the low quadrupole and the alignment of the low multipoles were in tension with the standard model of cosmology, and that while these anomalies could be statistical flukes, their persistence across different datasets and analysis methods made them interesting. That is scientists speak for, we don't know what this is, and it's kind of freaking us out. And Planck is not a small instrument. The Planck satellite was a marvel of engineering, a telescope that orbited the Sun at the L2 Lagrange point, 1.5 million kilometers from Earth, shielded from sunlight by a special screen, cooled to temperatures close to absolute zero to minimize thermal noise, and equipped with detectors so sensitive they could measure temperature differences of a millionth of a Kelvin. The data from Planck represents the most precise measurement of the CMB ever achieved, and it confirmed the axis of evil anomaly. So where does that leave us? Let's take stock of what we know. We have an anomaly in the CMB, a large-scale alignment of temperature fluctuations across the sky, pointing in a specific direction that coincides with the geometry of our solar system. This anomaly has been seen in multiple independent datasets, including the most precise CMB measurement ever made. It has a statistical significance that is difficult to explain by chance alone, and it poses a genuine challenge to the cosmological principle, which is the foundation of modern cosmology. And yet, it could still be a statistical fluke. It could still be some subtle systematic error that nobody has identified yet. It could be the result of some complex foreground contamination that has not been properly accounted for. This uncertainty is not a weakness of science. It is science working exactly as it should, carefully and honestly and without jumping to conclusions. But let's say, just for a moment, that the axis of evil is real. Let's imagine that when future, even more powerful experiments look at the CMB with even greater precision, the anomaly remains, stubborn and unexplained, precisely where it is. What would that mean? What are the possible explanations, and what do they tell us about the nature of the universe? This is where things get truly extraordinary, because the possible explanations for a real axis of evil range from the mundane to the mind-bending, from the merely puzzling to the cosmologically revolutionary. Let's start with the most conservative explanation. One possibility is that the alignment is related to some large-scale structure in our local universe, some enormous concentration of matter that is affecting the CMB signal. We know that matter can distort the CMB through a process called the integrated Sachs-Wolf effect, where photons gain or lose energy as they pass through large gravitational potential wells. Could there be some enormous cosmic structure in the direction of the axis of evil that is subtly modifying the CMB signal in a way that creates the appearance of an alignment? Some researchers have pointed to the Virgo cluster as a potential culprit. The Virgo cluster is a dense concentration of galaxies about 53 million light-years from Earth, and it happens to lie roughly in the direction of the axis of evil. Could the gravitational influence of the Virgo cluster be causing the observed alignment? The problem with this explanation is one of scale. The integrated Sachs-Wolf effect is known to produce signals in the CMB, but the alignment in the axis of evil is a feature at the largest angular scales, corresponding to structures spanning billions of light-years. The Virgo cluster, while enormous by human standards, is too small and too close to explain an effect at these scales. You would need something far more massive and far more distant to create this kind of imprint on the CMB. So let's go to the next level of explanation. What if the alignment reflects something about the topology of the universe, the actual shape of the cosmos on the largest scales? This is a remarkable idea. We tend to imagine the universe as infinite, stretching in all directions without end. But what if it isn't? What if the universe has a finite size and a specific shape, like a giant cosmic donut or a cosmic soccer ball? Topologically speaking, mathematicians call these spaces multiply-connected manifolds, spaces that have a finite size but no edges or boundaries, because they wrap around on themselves. If the universe is finite and has a specific topology, then light traveling in one direction could eventually wrap around and come back from the other direction. This would create patterns in the CMB that are correlated in specific ways, depending on the shape of the universe. Some of these correlations might look like large-scale alignments in the temperature fluctuations. The topology hypothesis for the axis of evil is not just speculation. Several serious cosmologists have investigated it. In 2003, shortly after the first WMAP data release revealed the anomalies, researchers including Jean-Pierre Luminet and colleagues published a paper in the journal Nature proposing that the universe might have the topology of a Poincare dodecahedral space, a kind of cosmic football, and that this could explain the low power in the CMB quadrupole. This hypothesis generated enormous excitement in the scientific community, partly because it was such a beautiful mathematical idea, and partly because it seemed to offer a concrete explanation for a puzzling anomaly. Subsequent WMAP data allowed scientists to test this hypothesis more rigorously, looking for specific patterns called circles in the sky that should appear if the universe has a dodecahedral topology. The results were mixed. Some studies found hints of these circles, others did not, and the consensus at the moment is that the dodecahedral space hypothesis has not been confirmed. But the broader idea that the axis of evil might reflect the topology of the universe remains alive and interesting. Let's go even deeper. What if the alignment doesn't reflect any structure in the universe, but rather a property of space and time itself? What if the universe is not just finite but actually anisotropic, fundamentally different in different directions? This would be a much more radical idea. It would mean throwing out the cosmological principle entirely, at least in its isotropy component. And there are actually cosmological models that allow for this. They are called anisotropic cosmological models, and one of the most studied is the Bianchi models, named after the Italian mathematician Luigi Bianchi, who classified different types of homogeneous but anisotropic spacetimes in the late 19th century. In a Bianchi universe, the expansion of the universe is different in different directions, creating a kind of cosmic stretching that would leave a distinctive imprint on the CMB. Researchers have studied whether adding a Bianchi component to the standard model could explain the large-scale CMB anomalies, and some have found that certain Bianchi models can reproduce features that look like the axis of evil. But this explanation comes with a heavy price. If the universe is truly anisotropic in the way required to explain the axis of evil, then virtually all of modern cosmology would need to be revised. The equations would change. The age of the universe might change. The composition of the universe might need to be re-evaluated. It would be a scientific revolution on the scale of Copernicus or Einstein. And then, of course, there is the most exotic explanation of all, the one that is simultaneously the most speculative and the most tantalizing. What if the axis of evil is a signal from another universe? You read that right. Another universe. We live in an era when the idea of a multiverse has moved from pure science fiction into serious theoretical physics. Many cosmological models, particularly those based on the theory of inflation, predict that our universe is just one bubble in an enormous, possibly infinite foam of universes, each created by a quantum fluctuation during an eternal inflationary process. Most of these universes would be completely separate from ours, unable to interact or communicate in any way. But there is a possibility, suggested by some theorists, that in the early moments of our universe's existence, it might have collided with another bubble universe, leaving an imprint on the CMB. The idea of a bubble universe collision is genuinely extraordinary. Imagine two soap bubbles floating through the air and touching each other. At the point of contact, they leave an impression on each other's surface. A collision between bubble universes would be something like that, but on an incomprehensibly larger scale. And if such a collision occurred, it might leave a distinctive signature in the CMB, a circular region of the sky with specific properties. Some researchers have looked for signs of bubble universe collisions in the CMB data. In 2010, a team led by Stephen Feeney published a paper claiming to have found hints of 4 possible bubble universe collision signatures in the WMAP data. Subsequent analysis with Planck data was less conclusive, and the scientific community has not reached a consensus that these signatures are real. But the fact that scientists are seriously looking for them, seriously testing whether the CMB carries the fingerprints of a cosmic collision with another universe, is remarkable in itself. Now, here is a question worth sitting with. What would it do to your understanding of existence, of your own place in the cosmos, if it turned out that the axis of evil was a scar left by a collision between our universe and another? What would it mean to know that beyond the farthest reaches of space, in a direction you can point to on a map, there is another universe, another reality, perhaps with its own physical laws and its own history? How would that change the way you think about what it means to be here, in this universe, on this planet, in this moment? These are not rhetorical questions. They are the kinds of questions that the axis of evil is actually forcing cosmologists to ask, and the fact that serious, tenured, Nobel-caliber scientists are debating them in the pages of peer-reviewed journals is one of the most remarkable things about the world we live in. But let's return to Earth for a moment, because the debate about the axis of evil is not just philosophical. It is intensely practical. It involves data, instruments, methods, and people, brilliant, passionate, sometimes infuriating people who have dedicated their careers to understanding the universe and who do not agree about what the data is telling them. The saga of the axis of evil is also, in part, a story about the sociology of science, about how scientists deal with anomalies that challenge their preferred models, about the tension between conservatism and revolution in the pursuit of knowledge. When the WMAP anomalies were first published and Kate Land and Joao Maguejo coined the phrase axis of evil in 2005, the reaction in the cosmological community was complex. Some scientists took the anomaly very seriously and immediately began trying to explain it. Others dismissed it as a statistical curiosity, a look elsewhere effect that would eventually be explained away by better data. And a few argued that even if it was real, it wasn't necessarily a problem for the standard model. It could just be a rare but not impossible fluctuation. Joao Maguejo himself is a fascinating and somewhat controversial figure in modern cosmology. Born in Portugal, educated at Cambridge, and based at Imperial College London, he is known for his willingness to challenge orthodoxy and propose radical ideas. He is one of the proponents of varying speed of light cosmology, the idea that the speed of light might not have been constant throughout the history of the universe, a hypothesis that most cosmologists find deeply uncomfortable and that has attracted intense criticism. His willingness to engage with uncomfortable ideas, and his flair for memorable language, made him the perfect person to coin the phrase axis of evil, even if it also made him easy to dismiss as a provocateur. But dismissing Maguejo doesn't make the anomaly go away. The axis of evil is not his finding alone. It has been studied, analyzed, contested, and reanalyzed by dozens of groups around the world using different methods and different data sets. And it keeps coming back. One of the most thorough and recent analyses of the large-scale CMB anomalies was published by the Planck collaboration in 2020, based on the final and most complete Planck dataset. The Planck paper on isotropy and statistics confirmed that the large-scale anomalies, including the low quadrupole power and the alignment of the low multipoles, remain in the Planck data. The team was careful to note that these anomalies have a probability of occurring by chance in the standard cosmological model of somewhere between 1 and a few percent, depending on the specific statistical measure used. They concluded that the anomalies are present and unexplained, but not conclusive evidence against the standard model. 1% to a few percent. Think about what that means. If you repeat an experiment 100 times, you expect a result this unusual to occur by chance just once or twice. That's not the kind of probability that makes a scientist say there is definitely something wrong with a standard model. But it's also not the kind of probability that makes you shrug and move on. It's the kind of probability that keeps you up at night, that makes you double-check your work, that makes you wonder if the universe is trying to tell you something. And here is where the story gets even more interesting, because the axis of evil does not stand alone. It is part of a growing collection of anomalies in the CMB and in large-scale structure data that are each individually explicable as chance fluctuations, but which together paint a picture that is increasingly difficult to dismiss. One of these anomalies is called the cold spot. In the southern sky, in the direction of the constellation Eridanus, there is a region of the CMB that is significantly colder than the surrounding area. The cold spot is not just slightly cold. It is about 70 microkelvins colder than the average CMB temperature, and it spans an angular size of about 5 degrees on the sky. Statistical analyses suggest that a cold spot of this size and depth has about a 1 in 10,000 chance of occurring by chance in the standard cosmological model. The cold spot has attracted enormous attention. Some researchers have proposed that it is evidence of a vast cosmic void, a supervoid, an enormous region of space that contains far fewer galaxies than average, creating a gravitational potential well that causes CMB photons to lose energy as they pass through it. In 2015, a team led by Istvan Saputty found evidence for a supervoid about 1.8 billion light-years across in the direction of the cold spot. This supervoid is one of the largest known structures in the universe, and if it is causing the cold spot, it would represent a remarkable discovery about the large-scale structure of the cosmos. But the supervoid hypothesis has its critics. Some analyses suggest that the supervoid, while real, is not large or empty enough to fully explain the cold spot. And even if the supervoid does explain the cold spot, the question of why such an enormous void exists is itself a puzzle that the standard cosmological model struggles to answer. Other CMB anomalies include the hemispherical power asymmetry, a tendency for the CMB temperature fluctuations to have slightly more power in one hemisphere of the sky than the other, like one side of the cosmos being slightly louder than the other. There is also the parity asymmetry, a tendency for the CMB to prefer certain mirror image patterns over others. Each of these anomalies is individually marginal, but together they tell a story. And here is the most uncomfortable part of that story. These anomalies are not random. They don't point in different directions, scattered across the sky like leaves thrown in the wind. They are related. The axis of evil, the cold spot, the hemispherical power asymmetry, and the parity asymmetry all seem to be oriented along similar directions in the sky, all roughly aligned with a common axis. This coherence, this conspiracy of anomalies all pointing in the same direction, is what truly elevates the axis of evil from a quirky statistical footnote to a potentially profound discovery. Think about that. You've got multiple independent anomalies in the CMB, each statistically unusual in its own right, and they're all aligned along the same axis. The probability of that happening by chance is much smaller than the probability of any single anomaly occurring by chance. It's as if you found not just one needle pointing north, but several needles, each pointing north, and they were supposed to be random. At some point, you stop thinking about chance and start wondering about magnets. Now let's talk about what the axis of evil means for the most fundamental ideas in cosmology, because this is where the stakes become truly astronomical. The cosmological principle, as we discussed, is the bedrock of modern cosmology. It is what allows cosmologists to write down simple equations that describe the entire universe. Without it, cosmology becomes incomprehensibly complicated. Every point in the universe would be different, every direction would have different properties, and the simple, elegant models that have given us so much understanding would collapse into a chaos of complexity. Inflation, the theory of rapid exponential expansion in the first moments of the universe's life, is supposed to be the mechanism that enforces the cosmological principle. Inflation was proposed in the early 1980s by Alan Guth, a theoretical physicist at MIT, to solve several problems with the standard Big Bang model. One of these problems was called the horizon problem. Why does the CMB look the same in all directions when regions of the sky that are far apart were supposedly never in contact in the early universe? How did opposite ends of the cosmos know to have the same temperature? Inflation solved this by proposing that the universe underwent an enormous expansion, inflating from a tiny patch that was in thermal equilibrium into the vast cosmos we see today. During this inflation, any primordial irregularities or anisotropies would be stretched out to scales far larger than the observable universe, leaving the universe smooth and isotropic on any scale we can observe. If the axis of evil is real, it suggests that inflation did not completely smooth out all structure. Something survived. Something left a mark on the largest scales of the universe that inflation was supposed to have erased. And that implies that either inflation is wrong or incomplete, or happened in a way that is very different from the standard models. This is not a small thing. Inflation is one of the most successful theories in modern cosmology. It makes predictions that have been confirmed with extraordinary precision by CMB measurements. Predictions about the shape of the universe, the scale of the temperature fluctuations, the statistical properties of the fluctuations. It is hard to argue with its successes, but the large-scale anomalies are among the places where its predictions seem to fail, and that failure, if confirmed, would demand an explanation. Some theorists have proposed modified versions of inflation that could produce large-scale anomalies. One idea is that inflation lasted for only a finite amount of time, just long enough to solve the horizon problem, but not long enough to erase all structure from a pre-inflationary state. If the universe had some preferred direction or anisotropy before inflation, and if inflation was short enough, that pre-inflationary structure might have survived and be visible today as the axis of evil. This idea has a wonderful name. It is sometimes called the fingerprint of the pre-inflationary universe. It suggests that embedded in the oldest light in the cosmos, there is a message from a time before the Big Bang as we normally understand it. A message from a state of the universe so ancient and so alien that we have no direct way of accessing it except through these faint, subtle patterns in the CMB. Another modification to inflation that has been proposed to explain the large-scale anomalies involves adding extra fields to the inflationary model, fields that are anisotropic or that have a preferred direction. These models are called vector field inflation or axion inflation or various other exotic names, and they are mathematically complex and not widely accepted. But they represent serious attempts to accommodate the axis of evil within a theoretical framework, rather than simply wishing it away. Let's step back and think about the human dimension of this story. Because science is not done by equations. It is done by people. And the debate about the axis of evil has been conducted by some of the most brilliant and colorful characters in modern science. George Smoot, who shared the Nobel Prize for the COBE results, famously described the CMB temperature fluctuations as the face of God, the imprint of the initial conditions that gave rise to everything we see. He was a towering figure in CMB cosmology, known for his intensity and his drive. When anomalies were found in the COBE data, Smoot and his team worked tirelessly to determine whether they were real or instrumental artifacts. John Mather, Smoot's co-laureate, was the project scientist for COBE and later for the James Webb Space Telescope. He is known for his precision and his careful, methodical approach to science. For both of these men, the CMB was not just data. It was a portal into the deepest secrets of the universe. Chuck Bennett, the principal investigator of the WMAP mission, led the team that first saw the large-scale anomalies in clear detail. Bennett has been a persistent voice for scientific caution about the anomalies, noting that many of them are at the boundary of statistical significance and could be explained by systematic errors or the look elsewhere effect. He has been an important counterweight to more sensational interpretations of the data. Andre Linde, one of the pioneers of inflationary cosmology, has spent decades building and refining the theoretical framework that the axis of evil threatens to undermine. Linde's work on chaotic inflation, which is one of the most mathematically elegant and physically motivated models of inflation, led directly to the multiverse concept. He has engaged seriously with the large-scale anomalies and their implications for inflationary models. And then there is the broader community of cosmologists, hundreds of them around the world, analyzing data, building models, running simulations, arguing at conferences and in journal papers about what the axis of evil means. This is science at its most alive and most human, a community of brilliant people engaged in a collective project of understanding reality, impeded by the limits of their instruments, their imaginations, and their mathematical tools. Now let's talk about where this story goes next, because the axis of evil is not a settled question. The debate is ongoing, and the coming years promise to bring new data and new insights that will either confirm or challenge its reality. One of the most important future experiments is the Simons Observatory, a ground-based CMB telescope being built in the Atacama Desert in Chile. The Simons Observatory is designed to measure the CMB's polarization, the orientation of the light waves, with unprecedented precision. CMB polarization is a different probe of the early universe than temperature, and it could provide independent confirmation or refutation of the large-scale anomalies. If the axis of evil is real and reflects a genuine property of the universe, it should leave a signature in the polarization data as well as the temperature data. Another major future experiment is CMB-S4, a proposed ground-based observatory that would use an array of more than 500,000 superconducting detectors to measure the CMB with extraordinary sensitivity. CMB-S4 would not just confirm or deny the axis of evil. It would map the CMB in such extraordinary detail that it would either reveal the physics behind the anomalies or constrain them so tightly that they could be definitively attributed to chance. There is also the LightBird satellite, a Japanese-led mission planned for launch in the late 2020s, which would measure the large-scale polarization of the CMB from space with a sensitivity designed to detect the faint signal of inflationary gravitational waves. LightBird would also provide new data on the large-scale temperature fluctuations and could shed new light on the axis of evil. These are not distant dreams. They are planned, funded, and in various stages of construction. The data they will produce will transform our understanding of the CMB and potentially resolve, once and for all, the question of whether the axis of evil is a measurement artifact or a genuine feature of the universe. But here is a thought that should make you pause. What if the new data confirms the axis of evil? What if every new instrument that looks at the CMB sees the same alignment, the same low quadrupole, the same conspiracy of anomalies pointing in the same direction? At what point does the scientific community stop calling it an anomaly and start calling it a discovery? At what point does the evidence become strong enough to say, definitively, that the standard model of cosmology is incomplete, and that the universe has a structure or a history that we do not yet understand? That moment has not arrived yet, but it could. And if it does, the implications for cosmology would be comparable to the Copernican revolution, to the realization that Earth is not the center of the universe, or to Einstein's realization that space and time are not fixed and absolute but dynamic and relative. It would be a paradigm shift of the first order. And here is the really interesting part of that scenario. A paradigm shift in cosmology would not just affect scientists. It would affect all of us. Because our understanding of the universe, of our place in it, of what it means for the cosmos to have a beginning and an eventual end, these are not just scientific questions. They are existential questions. They touch on the deepest human desire to understand who we are and where we come from and what the universe is. The axis of evil, if real, would tell us that the universe is not the simple, symmetric, elegant thing we thought it was. It would tell us that the cosmos has a direction, a spine, an axis. It would tell us that something happened in the very beginning of time, something we do not yet understand, that left a mark on the largest structures of the universe. And it would invite us to wonder what that something was, and whether understanding it might unlock secrets about the nature of reality that are currently beyond our imagination. Let's explore another dimension of this story, one that doesn't often get talked about in the popular press, but which is fascinating in its own right. The axis of evil has a connection to one of the deepest and most troubling questions in philosophy and cosmology: the anthropic principle. The anthropic principle, in its simplest form, says that the universe must be compatible with the existence of observers like us, because if it weren't, we wouldn't be here to observe it. This seems almost trivially true, but it has profound implications. Some cosmologists use the anthropic principle to explain why the universe has the specific properties it has, properties that are necessary for the existence of stars, planets, and life. They argue that we live in a universe with these properties because we couldn't live in a universe without them. And if the multiverse is real, there are many universes with different properties, and we inevitably find ourselves in one of the rare ones compatible with our existence. Now, what does the anthropic principle have to do with the axis of evil? Here's the intriguing connection. The axis of evil appears to be aligned with the geometry of our solar system. If this alignment is real and not a coincidence, some theorists have speculated that it might reflect a kind of anthropic selection effect, a cosmic situation in which observers are more likely to find themselves in regions of the universe where certain alignments exist, perhaps because those regions are more likely to produce the conditions necessary for life. This is a deeply speculative idea, and most cosmologists are skeptical of it. But it raises a profound question that you can ask yourself right now. Is it possible that our position in the universe, our location in space and time, is not as arbitrary as we think? Is it possible that the universe, or the multiverse, has a structure that makes certain positions more likely to be inhabited by observers? And could the axis of evil be a clue to that structure? These questions are on the edge of what science can currently address. They blend cosmology with philosophy and with the deepest questions of consciousness and observation. They are questions that the axis of evil, by its very existence, forces us to confront. Now let's go back even further in time, back before the axis of evil was discovered, back to the intellectual history that created the framework within which this anomaly is understood. Because the axis of evil is not just a scientific discovery. It is the product of a particular way of thinking about the universe, a way that developed over centuries and involved some of the greatest minds in human history. The idea that the universe is the same in all directions, isotropic, goes back at least to the Copernican revolution of the 16th century. Before Copernicus, the dominant Western view was that Earth was the center of the universe, with everything else revolving around it. This geocentric model was not just an astronomical hypothesis. It was a cosmological and philosophical worldview in which humanity's home was the central, special, most important place in all of creation. Copernicus shattered that worldview by proposing that the Sun, not Earth, was at the center of the solar system. This was a profound blow to human cosmic self-importance, the first step in a long process of decentering humanity from the universe. Galileo's observations with his telescope confirmed and extended the Copernican view, and eventually Newton synthesized it all into a unified mechanical picture of the cosmos. But it was the work of the 20th century that truly completed the dethronement of Earth from any special cosmic position. Edwin Hubble's discovery that the Milky Way is just one of billions of galaxies, and that these galaxies are all moving away from each other, combined with Einstein's General Relativity, led to the Big Bang model of the universe. And the Big Bang model, with its cosmological principle, said definitively that no position and no direction in the universe is special. We are ordinary. Our position is typical. The universe looks the same from everywhere and in every direction. The axis of evil, if real, would be the first crack in this picture of cosmic democracy. It would suggest that there is, after all, a special direction in the universe, an axis, a spine, a preferred orientation. It would not restore Earth to the center of the cosmos, but it would do something almost equally unsettling. It would say that the universe has a structure that we do not understand, that the Copernican principle in its strongest form, the cosmological principle, may not be entirely correct. This is why the discovery was named the axis of evil, and not just an interesting anomaly. The name captures the existential threat it poses to the foundational assumptions of modern cosmology. It is evil because it is dangerous. It is evil because if it is real, it might undo decades of beautiful, successful science. And yet, there is something thrilling about that. Because science is not supposed to be a closed book. It is not supposed to be a collection of eternal truths that can never be revised. The history of science is a history of paradigm shifts, of moments when something unexpected forced a complete rethinking of our most fundamental ideas. The photoelectric effect led to quantum mechanics. The perihelion precession of Mercury led to general relativity. The expansion of the universe led to the Big Bang model. In each case, an anomaly, something that didn't fit the existing picture, was the seed of a scientific revolution. The axis of evil might be the next such seed, or it might not. It might turn out to be an artifact, a glitch, a statistical ghost that disappears when the data improves. But the process of finding out is itself one of the great adventures of the human mind, and we are living in the middle of it. Now, let's talk about something that rarely gets discussed in the context of the axis of evil, but which is absolutely crucial for understanding the full picture. Let's talk about dark energy. Dark energy is the name given to the mysterious force that is causing the expansion of the universe to accelerate. Discovered in 1998 by two independent teams of astronomers studying distant supernovae, dark energy has since been confirmed by many different lines of evidence, including the CMB. It makes up approximately 68% of the total energy content of the universe, far more than ordinary matter or dark matter, and we have essentially no idea what it is. The standard model of cosmology assumes that dark energy is uniform, the same everywhere in the universe, and constant in time, not changing as the universe evolves. This assumption is encapsulated in the cosmological constant, a term that Einstein originally introduced into his equations to produce a static universe, later removed as a mistake when the expansion of the universe was discovered, and then reintroduced when dark energy was found. Einstein called the cosmological constant his biggest blunder, but it turned out to be a profound insight. But what if dark energy is not uniform? What if it has a direction, a gradient, a preferred orientation? What if dark energy is not a cosmological constant but a dynamical field that varies across space? If dark energy is anisotropic, if it pushes the universe to expand faster in some directions than others, it could potentially explain the axis of evil. An anisotropic dark energy field would create large-scale patterns in the universe that could look like the alignment of the CMB quadrupole and octopole. It would also leave other signatures in the distribution of galaxies, in the patterns of cosmic expansion, that future surveys might be able to detect. This is not a mainstream idea, and it would require an even more radical revision of our cosmological models than most of the other explanations for the axis of evil. But it is being explored by theorists, and it illustrates the breadth of the scientific imagination that the axis of evil has provoked. Dark energy is one of the great unsolved mysteries of modern physics. The fact that it might be connected to the axis of evil, that the largest anomaly in the CMB might be related to the most pervasive and mysterious force in the universe, is a possibility that should make your head spin. And it should make you appreciate that the universe is far stranger and far richer than any of our current models can capture. Here is a question worth pondering. We live in a universe dominated by something we cannot see, cannot measure directly, and cannot explain. Dark energy makes up more than 2/3 of everything there is, and we are essentially clueless about its nature. Doesn't that say something profound about the limits of human knowledge? And doesn't the axis of evil, this strange alignment in the oldest light of the cosmos, suggest that those limits might be even more severe than we thought? Let's shift gears now and think about the axis of evil in the context of some of the most exciting ideas in modern theoretical physics, ideas that could radically change our understanding of the universe if they turn out to be correct. String theory is the leading candidate for a theory of everything, a single mathematical framework that would unify quantum mechanics and general relativity, the two pillars of modern physics that currently refuse to cooperate with each other. String theory is extraordinarily complex and has not yet made predictions that can be definitively tested by experiment. But it has a remarkable feature. It predicts not just one universe, but an almost inconceivably vast landscape of possible universes, each with different physical laws, different dimensions, different fundamental constants. In string theory's landscape, our universe is just one of perhaps 10 to the power of 500 possible universes, a number so large it makes the number of atoms in the observable universe look like a rounding error. Most of these universes would be hostile to life as we know it. Our universe, with its particular set of physical constants that allow stars to burn and carbon to form and life to evolve, would be just one rare pocket of habitable cosmos in an enormous, mostly inhospitable landscape. In this framework, the axis of evil might have an explanation rooted in the initial conditions of our particular bubble of spacetime. Perhaps our universe was born with a slight anisotropy, a preferred direction, that was set by the specific quantum fluctuation or string landscape transition that gave rise to it. Perhaps that anisotropy was amplified during inflation or preserved at the largest scales. And perhaps what we see as the axis of evil is the residual signature of our universe's peculiar birth within the string landscape. This is deeply speculative, and most physicists would be the first to admit that. We are a long way from being able to test any of this with current or near-future experiments. But the intellectual richness of these ideas, the way they connect the smallest scales of quantum physics with the largest scales of cosmology, is one of the things that makes physics so endlessly fascinating. There is also the question of quantum cosmology, the attempt to apply the principles of quantum mechanics to the universe as a whole. In quantum cosmology, the universe can be in a superposition of states, a quantum mechanical mixture of different possible configurations. The wave function of the universe, a concept introduced by physicists John Wheeler and Bryce DeWitt in the 1960s and developed by Stephen Hawking and James Hartle in the 1980s, describes the probability of the universe being in any particular state. Could the axis of evil be a reflection of the quantum state of the universe? Could the alignment in the CMB be a consequence of the specific quantum mechanical conditions in which the universe was created? These ideas are fascinating but extremely difficult to make mathematically precise and testable. They represent the frontier of theoretical cosmology, the place where imagination and mathematics collide with a hard wall of testability. Let's now take a step back and think about the axis of evil in a broader cultural context, because scientific anomalies do not exist in isolation. They are discovered by people who live in a culture, who have assumptions and biases, and the way those anomalies are received by the broader public says something interesting about our collective relationship with science. The axis of evil has captured the public imagination in a way that most CMB anomalies have not. The name helps, of course. The axis of evil is a more memorable and dramatic label than the quadrupole-octopole alignment. But there is something deeper at work. The axis of evil touches on questions that human beings have always found compelling. Is there a direction to the universe? Is there a center? Are we special? These are questions that resonate across cultures and throughout history, questions that religion and philosophy have grappled with long before science got involved. In many religious and spiritual traditions, the universe has a preferred direction or a cosmic axis. The Hindu concept of Mount Meru, the axis mundi of the cosmos. The Norse world tree, Yggdrasil, connecting different realms of existence. The Christian idea of heaven above and earth below. The shamanic concept of a cosmic axis connecting the terrestrial world with the spirit world. These are all expressions of a deep human intuition that the universe is not uniform, that it has a structure, a spine, a preferred direction. The fact that modern cosmology stumbled upon something called the axis of evil, an actual alignment in the universe, is the kind of thing that makes you wonder whether our deepest intuitions about reality sometimes catch a glimpse of something true, even if the mechanism is utterly different from what any tradition imagined. Of course, science demands more than intuition. It demands evidence, reproducibility, statistical rigor. And the axis of evil, as we have discussed, is still contested territory. But the conversation between the scientific anomaly and the deep human need to find meaning in the structure of the universe is itself a fascinating story, one that illuminates something important about why we do science and what we hope to find. Now let's go even deeper into the physics, because to fully appreciate the axis of evil, we need to understand something about how cosmologists actually measure the CMB and why those measurements are so extraordinarily challenging. The CMB radiation arrives at Earth from all directions simultaneously. It fills the entire sky. Measuring it requires building instruments that can detect microwave radiation with extraordinary precision, distinguish it from all other sources of microwave emission, and map its temperature and polarization across the full sky. This is a task that is technically demanding in ways that are hard to overstate. The COBE satellite, launched in 1989, was the first instrument capable of mapping the full sky CMB at the level of the tiny fluctuations. But COBE had a resolution of about 7 degrees, meaning it could only see temperature variations on angular scales of 7 degrees or larger. That is quite coarse. The full moon subtends only half a degree on the sky. So COBE was seeing very broad, smooth patterns in the CMB, not the fine details. WMAP, launched in 2001, had a resolution of about 12 arc-minutes at its best frequency, which is 20 times finer than COBE. This allowed WMAP to see the acoustic peaks in the CMB power spectrum, the characteristic patterns of temperature fluctuation that are the direct imprint of sound waves in the early universe. These acoustic peaks are one of the most beautiful and precisely predicted features of standard cosmology, and their confirmation by WMAP was a triumph of the standard model. But here is the challenge. The large-scale anomalies, the quadrupole and octopole alignment, the axis of evil, are at the very largest angular scales, scales of tens of degrees or more. And at these large scales, the statistical power of any CMB measurement is fundamentally limited by what is called cosmic variance. Because we can only observe one universe, we can only measure the CMB temperature at each point in our sky once. The largest patterns in the CMB are described by just a handful of independent measurements, determined by the smallest possible number of multipole moments. This means that even with a perfect instrument, the statistical uncertainty on the largest scale patterns is irreducibly large. In other words, even Planck, even the most perfect CMB satellite imaginable, cannot completely resolve the question of whether the axis of evil is a real feature of the universe or a statistical fluke, because at the largest scales, the universe itself limits how much we can know. This is called the cosmic variance limit, and it is one of the most profound and humbling constraints in cosmology. Imagine trying to understand the entire color palette of an artist by looking at just a small corner of a single painting. You might see patterns and colors, but you would never be entirely sure whether what you see reflects the artist's overall style or is just a coincidence of the particular corner you're examining. That is roughly the situation cosmologists face with the largest scale features of the CMB. This cosmic variance problem does not mean we are helpless. It means that to better constrain the large-scale anomalies, we need to look at different probes of the universe, probes that are not subject to the same limitations. One of these is the large-scale distribution of galaxies. If the universe has a genuine preferred direction, if the axis of evil is real, it should leave signatures not just in the CMB but in the three-dimensional distribution of galaxies. Galaxies should be distributed differently in the direction of the axis of evil than in the perpendicular direction. Large-scale galaxy surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the Future Euclid Satellite and the Rubin Observatory are producing and will produce maps of the galaxy distribution over enormous volumes of space, maps that could provide independent evidence for or against a cosmic anisotropy. Some analyses of existing galaxy survey data have found hints of large-scale anisotropies in the galaxy distribution. A controversial 2020 paper by Subir Sarkar and colleagues claimed to find evidence for an anisotropy in the distribution of quasars, the luminous cores of active galaxies, that is inconsistent with the cosmological principle. This claim was disputed by other researchers, but it added to the growing catalog of potential large-scale anomalies. The Euclid satellite, launched by the European Space Agency in 2023, is designed to map the shapes and distances of billions of galaxies across a large fraction of the sky. Over its mission lifetime, Euclid will produce the most detailed three-dimensional map of the universe ever made, allowing cosmologists to test the cosmological principle with unprecedented precision. If the universe has a preferred direction, Euclid might be the instrument that makes it impossible to deny. Similarly, the Vera C. Rubin Observatory, a ground-based telescope in Chile that began operations recently, will survey the southern sky repeatedly over a 10-year period, cataloging billions of galaxies and other astronomical objects. The data from the Rubin Observatory will be used to test cosmological models in many ways, including searches for large-scale anisotropies. So the next decade is going to be crucial. We are at a moment in history when the data that will either confirm or refute the axis of evil as a genuine feature of the universe is within our reach. The instruments are either being built or are already running. The data is coming. And when it comes, the question of whether the universe has an axis will be answered with a clarity and precision that current data cannot provide. And that is one of the most exciting things about living right now. We are alive at a moment when some of the deepest questions about the nature of the universe are about to be answered, or at least significantly clarified. The generation of scientists who are in graduate school right now, who are building these instruments and writing these computer codes and developing these statistical methods, they will be the ones who see the answer. And through the science they publish and the discoveries they announce, so will the rest of us. Now let's explore a dimension of the axis of evil that touches on one of the most profound debates in the history of science: the relationship between mathematics and physical reality. This might seem like a detour, but bear with me, because it illuminates something important about why the axis of evil is so troubling. When physicists and cosmologists build models of the universe, they use mathematics. They write down equations that describe how space and time behave, how matter and energy interact, how the universe evolved from its hot, dense beginning to the vast, cool, structured cosmos we see today. These equations have been extraordinarily successful. They have predicted phenomena that were later confirmed by observation, from the existence of gravitational waves to the accelerating expansion of the universe. But here is the thing about mathematics. It can describe many different possible universes, not just the one we live in. The equations of general relativity, for example, have solutions that describe universes that are rotating, universes that are expanding faster in one direction than another, universes with different topologies. The standard cosmological model, based on the cosmological principle, is just one of these solutions. It is the simplest solution that is consistent with the available data. But simplicity is not the same as truth. The fact that a simple, symmetric model explains most of the data does not mean the universe is actually simple and symmetric. It might just mean that the deviations from simplicity and symmetry are small enough that our instruments have not yet been able to detect them clearly, or that we have been looking for them in the wrong places. The axis of evil might be telling us exactly that. It might be telling us that the universe is more complex, more structured, more interesting than the simplest cosmological model assumes. It might be inviting us to consider solutions to Einstein's equations that are not perfectly isotropic, not perfectly homogeneous, but that have a richness and complexity that our current framework has been too blunt to capture. If that is the case, then the axis of evil is not just an anomaly to be explained away. It is a gift, an invitation to go deeper, to explore the full mathematical richness of our theories and see whether the universe is more complex and more beautiful than we thought. This perspective is not the majority view in cosmology today. Most cosmologists would prefer to explain the axis of evil within the standard framework, either as a statistical fluke or as the result of some physical effect they haven't yet identified. But the minority voice that says the axis of evil might point to genuinely new physics, to a richer and more complex universe than the standard model envisions, is not a voice that can or should be dismissed. Let's now take a moment to think about the process by which science deals with anomalies like the axis of evil, because this process is itself a fascinating story. When an anomaly is found in scientific data, the first response is usually skepticism. Scientists look for mistakes, for instrumental errors, for analysis mistakes, for the look elsewhere effect. This skepticism is healthy. It is how science protects itself from being led astray by coincidences or artifacts. The history of science is full of claimed anomalies that turned out to be errors, from the faster-than-light neutrinos claimed by the Opera experiment in 2011, which turned out to be caused by a loose cable, to the cold fusion claims of the late 1980s that could never be replicated. So when the axis of evil was first discovered in the WMAP data, the initial response of many cosmologists was to look for mundane explanations, and they found some plausible ones. The foreground contamination argument was the most compelling. If galactic emission was not perfectly removed from the CMB map, it could create artificial large-scale patterns. Different groups tried different foreground subtraction methods and got somewhat different results, which suggested that the foreground was indeed important. But as the data improved, as the analysis methods became more sophisticated, and as Planck provided an independent confirmation with lower foreground contamination, the anomaly persisted. It didn't get stronger, but it didn't go away either. And the scientific community has gradually shifted from trying to explain it away to trying to understand it. This shift is subtle but important. It represents a growing acceptance that the axis of evil is not just a mistake or an artifact, even if scientists are not yet ready to say it is definitely a real feature of the universe. It is now widely acknowledged as a genuine tension in the data, a place where the standard model is not performing as well as it should. And that acknowledgement, that willingness to sit with uncertainty and continue investigating rather than either dismissing the anomaly or overclaiming its significance, is science working at its best. It is the scientific method being applied honestly and rigorously to a question that is hard to answer with current data. One of the most interesting aspects of the axis of evil debate is how it highlights the tension between two different philosophies of scientific progress. On one side are the incrementalists, who believe that the standard model of cosmology is basically correct and that apparent anomalies like the axis of evil will eventually be explained within the existing framework by better data and more careful analysis. On the other side are the revolutionaries, who believe that anomalies like the axis of evil are symptoms of a deep flaw in the standard model, a flaw that cannot be patched with minor adjustments, but that requires a fundamental rethinking of our cosmological framework. Both philosophies have historical precedents. Sometimes incrementalism wins, and an anomaly turns out to be a minor correction to a basically correct theory. Sometimes revolutionism wins, and an anomaly turns out to be the first crack in a failing paradigm. We don't yet know which one the axis of evil is going to be. But the revolutionaries have a powerful argument on their side. The standard model of cosmology is not just facing the axis of evil. It is facing a whole collection of tensions and anomalies, from the Hubble tension to the S8 tension to the large-scale CMB anomalies. The Hubble tension, for those who aren't familiar, is the disagreement between the value of the Hubble constant measured from the CMB and the value measured from local astronomical observations. This disagreement has grown steadily in significance over the years and is now at a level of more than 5 sigma, which in physics is the conventional threshold for claiming a discovery. The Hubble tension might indicate that the standard model is wrong, or it might be the result of systematic errors in the measurements. But its persistence and growing significance cannot be ignored. Could the Hubble tension and the axis of evil be connected? Could they both be symptoms of the same underlying flaw in our cosmological model? Some researchers have speculated that an anisotropic expansion of the universe, of the kind that would produce the axis of evil, might also affect the measurement of the Hubble constant, creating the tension we observe. This is a speculative connection, but it is being explored, and it illustrates how different anomalies in cosmology might be clues to the same deeper truth. Let's now take a step back and appreciate the extraordinary intellectual achievement that is represented by our ability to detect and discuss the axis of evil at all. The fact that humans have built instruments sensitive enough to map the temperature of the universe at 1 part in 100,000 across the entire sky, and to compare that map with theoretical predictions in enough detail to notice an alignment of large-scale patterns, is a staggering accomplishment. The Wilkinson Microwave Anisotropy Probe was launched on a Delta II rocket in June 2001 and traveled to a position 1.5 million kilometers from Earth, where the gravitational pulls of the Earth and the Sun balanced to create a stable observing position. From there, it scanned the entire sky every 6 months for 9 years, accumulating data on the CMB with extraordinary precision. The team that operated WMAP processed and analyzed petabytes of data, developing new statistical tools and new analysis methods to extract the maximum information from the observations. The Planck satellite, launched by the European Space Agency in 2009, was an even more sophisticated instrument. It carried 2 sets of detectors, operating at different frequencies, that allowed scientists to distinguish the CMB from the various foreground signals contaminating it. Planck's detectors were cooled to temperatures within 1/10 of a degree of absolute zero, making them among the coldest objects in the universe outside of physics laboratories. The mission lasted until 2013, and the analysis of its data has continued for years, producing a series of landmark papers that have defined the current state of cosmological knowledge. These missions were not cheap or easy. WMAP cost about $150 million. Planck cost over 700 million euros. They required thousands of scientists and engineers, working for years to design, build, test, launch, operate, and analyze them. They were products of extraordinary human collaboration, spanning continents and decades. And all of this effort, all of this investment, all of this human ingenuity was aimed at a single goal: understanding the oldest light in the universe. Understanding the faint, ancient whisper from the edge of time. Understanding the cosmic microwave background. And in that CMB, hidden in the data, was the axis of evil. A pattern that nobody expected. A challenge to everything we thought we knew. A cosmic mystery that may be the most important clue about the nature of the universe ever discovered, or the most elaborate red herring in the history of science. Now let's talk about some of the specific scientists and papers that have shaped our understanding of the axis of evil, because the names and the stories matter. They make this abstract scientific debate real and human. The paper that gave the axis of evil its name was published by Kate Land and João Maguejo in 2005 in Physical Review Letters, one of the most prestigious journals in physics. The paper was titled The Axis of Evil, and it systematically analyzed the WMAP data to characterize the alignment of the low multipoles and its statistical significance. Land and Maguejo found that the alignment was significant at the level of about 1 in 200, meaning that if the universe were truly isotropic, you would expect to see this alignment by chance about once in every 200 realizations of a universe. Not impossible, but remarkable. The paper attracted immediate attention. It was not the first paper to notice the alignment, but it was the most vivid and quotable, partly because of the name and partly because of Maguejo's reputation for engaging with the public and the press in a way that more reserved scientists often do not. Earlier work by Max Tegmark, Angelica de Oliveira Costa, and Andrew Hamilton, published in 2003 shortly after the first WMAP data release, had already noted the alignment of the quadrupole and octupole and suggested that it was an unlikely coincidence in the standard cosmological model. Tegmark, who is a professor at MIT and one of the most prominent figures in modern cosmology, has continued to engage with these anomalies and their implications for cosmological models. In 2004, Copy, Huderer, Starkman, and Weeks published a detailed paper analyzing the WMAP data and confirming the alignment and the low quadrupole power, assigning it a probability of occurrence by chance of less than 1 in 1,000 in the standard model. These authors have been among the most persistent and rigorous advocates for taking the large-scale CMB anomalies seriously. Glenn Starkman, in particular, has given many talks and written many papers arguing that the axis of evil and related anomalies are genuine challenges to the standard model that cannot be dismissed as statistical flukes. On the other side of the debate, Eiichiro Komatsu, who led the WMAP data analysis team, and his colleagues have consistently argued that while the anomalies are real in the data, their statistical significance is uncertain due to the look elsewhere effect and the a posteriori nature of the analysis. Komatsu, who is one of the most precise and careful analysts in the field, has generally favored the conservative interpretation that the anomalies do not require physics beyond the standard model. This debate between Starkman and Komatsu, if you will, although it's actually a much broader debate involving dozens of scientists, represents the fundamental tension in the scientific community about the axis of evil. It is a debate about statistics, about the nature of evidence, about the balance between openness to new ideas and rigor in testing them. It is a debate that will only be resolved by better data, and that data is coming. One particularly interesting set of papers involves attempts to test the alignment using CMB polarization data rather than temperature data. Polarization is a different property of the CMB photons, related to the orientation of the electromagnetic waves. The polarization of the CMB is generated by the same physical processes that generate the temperature fluctuations, but it encodes somewhat different information. If the axis of evil is a real feature of the universe, it should be visible in the polarization data as well as the temperature data. The WMAP satellite measured CMB polarization, but with limited sensitivity at the large angular scales most relevant to the axis of evil. Planck measured the polarization more precisely, But even Planck's polarization measurements at the largest scales were dominated by noise and systematic errors. Future missions like LIGHTBIRD are specifically designed to measure the large-scale CMB polarization with the sensitivity needed to fully characterize the large-scale polarization signal and test whether the axis of evil anomaly is present in the polarization data. This is going to be a crucial test. If the axis of evil appears in both the temperature and the polarization data at similar angular scales and in similar directions, it will be very difficult to attribute to a systematic error or foreground contamination, because such artifacts would need to affect two independent measurements in exactly the same way. A confirmed alignment in both temperature and polarization would be strong evidence that the axis of evil is a real feature of the CMB, and by extension, of the universe. Let me tell you about another intriguing piece of the puzzle: the dipole repeller. In 2017, a team of researchers led by Yehuda Hoffman of the Hebrew University of Jerusalem published a paper in Nature Astronomy describing what they called the dipole repeller. We have known for decades that our local group of galaxies, which includes the Milky Way and Andromeda, is moving through space at about 600 kilometers per second relative to the CMB. This motion creates the dipole signal in the CMB, the biggest and most obvious pattern in the full sky map. The direction we are moving toward the Shapley supercluster, a massive concentration of thousands of galaxies, was already known. But the Hoffman team showed that we are also being repelled from an underdense region of the universe, a cosmic void in the direction of the constellation Gemini, which they call the dipole repeller. Our motion through space is not just driven by attraction toward the Shapley supercluster, but also by repulsion, or rather, by the push from the slightly less dense region behind us. Now, the dipole repeller is not directly the same thing as the axis of evil. The dipole is a local effect, related to our peculiar motion, and is not considered a cosmological signal in the same sense as the quadrupole and octopole. But the dipole repeller is interesting for the axis of evil story because it illustrates how large-scale structures in the universe, structures that are not predicted by the simplest cosmological models, can affect what we observe in the CMB. It suggests that the universe has large-scale structures that are more complex and more asymmetric than the standard model predicts, and it invites the question of whether the large-scale structures responsible for the dipole repeller might also be contributing to the axis of evil. Could there be a connection? Could the axis of evil be related not just to the topology of the universe or to the initial conditions of inflation, but to some enormous asymmetric structure in the large-scale distribution of matter that we haven't yet fully mapped? This is an intriguing possibility, and it is being investigated by researchers who are combining CMB data with large-scale structure surveys to look for correlations between the distribution of galaxies and the large-scale CMB anomalies. Now, here's something truly mind-bending that we haven't discussed yet, something that takes the axis of evil and places it in an even stranger context. There is a related anomaly in the CMB called the dipole modulation, or the hemispherical power asymmetry. This is the observation that the power of the CMB temperature fluctuations is slightly different in two opposite hemispheres of the sky. One hemisphere has slightly more fluctuation power than the other, as if the universe is slightly louder on one side than the other. This asymmetry is subtle, about a 3 to 4% difference in power between the two hemispheres, but it has been detected with statistical significance in both WMAP and Planck data. And here is the key point. The axis that divides the more powerful hemisphere from the less powerful hemisphere is roughly aligned with the axis of evil, the direction along which the quadrupole and octopole are aligned. So you have two different anomalies, the alignment of the low multipoles and the hemispherical power asymmetry, both pointing in roughly the same direction. This coherence is exactly what you would expect if there were a genuine physical explanation for both anomalies, some real property of the universe that is responsible for a preferred direction at the largest scales. And there are models that predict both anomalies simultaneously. One class of models involves a primordial spectrum of density fluctuations that is not perfectly scale invariant and isotropic, but that has a slight asymmetry, varying slightly in amplitude from one direction to another. Such an asymmetric spectrum would be generated by certain exotic inflationary models involving particular kinds of fields or particular kinds of potential energy landscapes for those fields. Another class of models involves a cosmic texture, a kind of large-scale defect in the universe that was created during a phase transition in the very early universe. Cosmic textures are topological defects, similar in some ways to the defects that form in a crystal when it solidifies too quickly, and some varieties could leave large-scale imprints in the CMB that look like the axis of evil. These are speculative ideas, and none of them has been confirmed. But the fact that multiple anomalies in the CMB are aligned with each other, and that there are physical models that can produce such alignments, means the axis of evil is not an isolated curiosity. It is part of a larger pattern that demands a coherent physical explanation. Think about what you know so far. You have a low quadrupole. You have an aligned quadrupole and octopole. You have a hemispherical power asymmetry. You have a cold spot. All of these anomalies exist in the same dataset, all confirmed by independent experiments, and all pointing roughly in the same direction. That level of coherence is hard to dismiss as pure coincidence. At this point, you might be wondering, has anyone proposed a single, unified explanation that accounts for all of these anomalies at once? The answer is, not yet, not convincingly. That is one of the greatest intellectual challenges in modern cosmology. Finding a single physical mechanism that can explain the low quadrupole, the alignment, the hemispherical asymmetry, and the cold spot simultaneously, within a framework that is otherwise consistent with the enormous successes of the standard cosmological model, is an enormously difficult problem. Some researchers have proposed that a combination of a modified inflationary model, which produces a slightly asymmetric spectrum of density fluctuations, combined with a specific large-scale structure effect, like a supervoid producing the cold spot, could explain most of the anomalies together. But these combined models tend to be complicated and have many free parameters, making it hard to test them decisively. The ideal situation would be to find a single, simple, elegant physical mechanism, something like a slight rotation of the universe at the beginning of inflation, or a specific topology, or a pre-inflationary state with a preferred direction, that naturally produces all of the observed anomalies as consequences. Finding that mechanism would be a discovery comparable in significance to any in the history of cosmology. And it is possible. Not certain, not even probable by current evidence, but possible. And the possibility of it keeps cosmologists engaged with the axis of evil even after decades of investigation. Let me now take you on a brief digression into a fascinating corner of the axis of evil story that involves not just the sky above us but the mathematics beneath us. Specifically, I want to talk about the role of supercomputer simulations in this investigation. Modern cosmology relies heavily on computer simulations. To understand the large-scale structure of the universe, to predict what the CMB should look like, to test different cosmological models against observations, scientists run enormous numerical simulations that model the evolution of the universe from the very early moments after the Big Bang to the present day. These simulations start with initial conditions, a set of random density fluctuations with specific statistical properties, and then evolve those conditions forward in time using the equations of general relativity, hydrodynamics, and gravity. The largest of these simulations are staggering in scale. The Millennium Simulation, run by the Virgo Consortium in 2005, modeled the evolution of 10 billion particles representing dark matter in a cosmic volume spanning 2 billion light-years on a side. Subsequent simulations, like the illustrious TNG simulation and the Euclid flagship simulation, have gone further, modeling both dark matter and baryonic matter, ordinary atoms and gas, with increasing sophistication. These simulations are used to test the axis of evil in a specific way. Scientists run thousands of simulated universes, each with the same physical parameters as the standard model but with different random realizations of the initial quantum fluctuations. They then look at how often, in these simulated universes, the large-scale CMB anomalies occur as large or larger than those observed in our universe. If the anomalies occur in only a small fraction of simulated universes, that is evidence that our universe is unusual. And that is precisely what the simulations show. The combination of anomalies seen in our CMB, the low quadrupole, the aligned quadrupole and octopole, the hemispherical asymmetry, occurs in only a small percentage of standard model simulated universes. Exactly what percentage is a matter of ongoing debate, but estimates generally range from less than 1% to a few percent, depending on how you define and measure the anomalies. 1% to a few percent. Not zero, not impossible, but unusual enough to make you take notice. And the key thing about the simulations is that they represent a rigorous, objective way of quantifying the improbability of the axis of evil in the context of the standard model. They are not subject to the same kind of a posteriori bias as simple statistical analyses, because you can define the specific anomalies you're measuring before you run the simulations and look at the results. When done properly, this approach gives a clean, unbiased estimate of how likely the observed anomalies are in the standard model. Some of the most compelling recent work on the axis of evil has used this simulation-based approach. Researchers like Dominic Schwartz, Dominique Erzadian, and others have pushed the analysis of large-scale CMB anomalies to new levels of rigor, developing more powerful statistical tools and running larger and more realistic simulations. Their work has confirmed the persistence of the anomalies and sharpened our understanding of their statistical significance. And yet, even with all of this rigor, the question remains unresolved. Because at the level of 1 to a few percent probability, we cannot definitively claim that something is wrong with the standard model. We need either a theoretical explanation that predicts the anomalies, or a reduction in their probability of chance occurrence to a much smaller level, or independent evidence from a completely different direction. All of this brings us to a very interesting and somewhat uncomfortable place. We are sitting with a collection of anomalies in the oldest light in the universe that have been seen by multiple independent experiments, confirmed by rigorous statistical analysis, and explored by some of the most brilliant minds in science. These anomalies are collectively strange enough to deserve a name, the axis of evil, and individually significant enough to have generated hundreds of peer-reviewed papers. And yet we cannot conclusively say what they mean. This is one of the things that makes the axis of evil genuinely fascinating. It is not a neatly resolved mystery. It is an open question, a living, breathing challenge to our understanding of the universe. And living with open questions, sitting with uncertainty without rushing to a premature conclusion, is one of the most important and difficult things that science requires. Let's now think about the implications of the axis of evil for our understanding of time, because there is a dimension of this story that we haven't fully explored, and it is one of the most profound. The CMB is not just a snapshot of the early universe. It is a window into the initial conditions of our cosmos. The patterns we see in the CMB, including the anomalies that make up the axis of evil, were set in the very first moments after the Big Bang, or even before the Big Bang as we normally understand it, during the inflationary epoch. Those patterns have been traveling through space, expanding with the universe, for nearly 14 billion years, and they have finally reached us. In a very real sense, looking at the CMB is a form of time travel. We are seeing light from the edge of time, from a moment so ancient that nothing we recognize as normal existed yet. No stars, no galaxies, no planets, no atoms, not even hydrogen atoms. Just a glowing, turbulent plasma, quantum fluctuations stretching across space, and the seeds of everything that would eventually become the cosmos. The axis of evil is embedded in that ancient light. If it is real, it was set in the beginning. Whatever created it, whatever physical process was responsible for the alignment we see today, it happened in the very first fractions of a second of the universe's existence, or perhaps even before. It has been waiting, preserved in the CMB, for nearly 14 billion years, for a species smart enough to build instruments sensitive enough to detect it. And we, in the early 21st century, are that species. We built those instruments. We detected that signal. We found the anomaly that was waiting for us in the oldest light in the universe. And now we are trying to understand what it means. That is a story worth being part of. That is a story worth telling. Let's think about the future. Not just the scientific future, with its new telescopes and satellites and simulations, but the intellectual future. How might the axis of evil change the way we think about the cosmos in the decades and centuries to come? If the axis of evil is confirmed as a real feature of the universe by future experiments, the most likely outcome is that cosmologists will construct new models that incorporate it. These models might involve modified inflation, non-trivial topology, or some other departure from the standard cosmological framework. These new models will make new predictions that can be tested with even more precise future observations, and gradually, through this cycle of prediction and testing, we will build a more complete understanding of the universe. If the axis of evil turns out to be a statistical fluke, a coincidence that happened to appear in our particular realization of the universe, then future data will show no compelling signs of a preferred direction in the universe. The large-scale anomalies will shrink in statistical significance as new data arrives, and eventually cosmologists will accept that the standard model is correct at the largest scales. The axis of evil will be remembered as an interesting moment in the history of cosmology, a reminder that data should always be taken seriously but interpreted with caution. But there is a third possibility, one that is perhaps the most exciting of all. The future data might not definitively resolve the question either way. The axis of evil might remain, stubbornly, at the borderline of statistical significance, neither going away nor becoming overwhelmingly significant. In this scenario, cosmologists will be forced to grapple with the anomaly indefinitely, without the clean resolution that either confirmation or refutation would provide. This third scenario is uncomfortable for science, which prizes clean, definitive answers. But it is also, in a way, the most honest acknowledgement of the cosmic variance limit, of the fundamental fact that we can only observe one universe and that some questions about that universe might be forever beyond our reach. If we are in this third scenario, the axis of evil might become the cosmological equivalent of the ship of Theseus, a question that perpetually invites new thinking and new analysis without ever quite being resolved. And that, while frustrating, is also a kind of intellectual richness that keeps science alive and vital. Now let's turn to something quite specific and quite interesting: the mathematical description of the CMB anomalies and what it tells us physically. When cosmologists decompose the CMB temperature map into spherical harmonics, they represent it as a sum of terms labeled by two numbers, L and M. The number L is called the multipole moment, and it describes the angular scale of the pattern. L equals 2 is the quadrupole, L equals 3 is the octupole, and so on. The number M describes the orientation of the pattern within each multipole moment. In a perfectly isotropic universe, the different M values for a given L should all have roughly the same power, randomly distributed. The overall power at each L is described by the CMB power spectrum, which tells you how much temperature variation there is on the angular scale corresponding to each L value. The standard cosmological model makes very precise predictions for this power spectrum, and WMAP and Planck have measured it with extraordinary precision, confirming the predictions with beautiful accuracy for most values of L. But at L equals 2, the quadrupole, the power is low, significantly lower than the standard model predicts. And when you look at the orientation of the quadrupole and octupole patterns on the sky, you find that certain orientations are preferred over others in a way that is not expected if the universe is isotropic. Specifically, the planes of the quadrupole and octupole patterns, the great circles on the sky around which most of the power in these modes is concentrated, are aligned with each other. They both point in the direction of the axis of evil. And the probability of this alignment occurring by chance in a truly isotropic universe is what makes the axis of evil interesting. But here's an additional subtlety. The alignment is not just between the quadrupole and octupole. It also involves the dipole, the L equals 1 mode, and possibly higher multipoles as well. The L equals 5 and L equals 6 modes also show some tendency to align with the axis of evil direction, although this is less significant statistically. The coherence across multiple multipole moments is what makes the alignment truly remarkable. Think about it this way. If you were playing music on a piano and you played several different notes, they would normally have no particular relationship to each other in terms of their timing or their pattern. But if all the notes you played were somehow synchronized, all vibrating in harmony, you would suspect that something was controlling them, some larger musical structure that coordinated the individual notes. That is roughly what the alignment of the CMB multipoles looks like. Different angular scales in the CMB are synchronized in their orientation, as if they are all responding to some larger structure or principle that we haven't yet identified. That analogy to music is not just poetic. The CMB actually has a musical structure. The acoustic peaks in the CMB power spectrum are literally the result of sound waves, compressions, and rarefactions in the early universe's plasma that were frozen in place when the universe became transparent. The CMB is like a photograph of a symphony orchestra at the moment of a particular chord, with the different angular scales corresponding to different harmonics of the fundamental sound that propagated through the young universe. And within that symphony, the axis of evil is a peculiar note, an off-key sound that doesn't fit the score. It is the universe playing a note that the standard model didn't write. Now let's explore the question of what the universe would look like if the axis of evil were not just an anomaly but the defining feature of the cosmos. Let's indulge in a moment of speculation, clearly labeled as such, and imagine a universe where the alignment is real and profound. In such a universe, space itself might have a preferred direction built into it from the very beginning. Perhaps the laws of physics are not perfectly isotropic, as we assume. Perhaps there is a subtle asymmetry in the way electromagnetic radiation, or even gravity, propagates in different directions. This would be an incredibly exotic scenario, violating the Lorentz symmetry that is the foundation of special relativity, but some theories of quantum gravity do allow for small violations of Lorentz symmetry at very high energies or very large scales. If such an asymmetry existed, and if it manifested at cosmological scales, it would leave a persistent, coherent signature in the CMB that would look exactly like the axis of evil. Future experiments designed to test Lorentz symmetry with cosmological data, like searches for direction-dependent modifications of the CMB power spectrum, could potentially test this idea. Or imagine a universe where the axis of evil is a remnant of the universe's rotation. Some cosmological models, inspired by the old idea of a Gödel universe, proposed by mathematician Kurt Gödel in 1949, involve a universe that rotates. A rotating universe would break the isotropic symmetry and create preferred directions. The CMB anomalies in such a universe might look like the axis of evil. Current constraints from CMB measurements limit the rotation rate of the universe, if it rotates at all, to be extraordinarily small. But the constraints are not zero, and some researchers have argued that a small residual rotation could be responsible for some of the observed anomalies. These are speculative ideas, but they are rooted in real physics and real mathematics, and they illustrate the range of physical scenarios that the axis of evil could be pointing us toward. Let's now talk about another fascinating connection: the relationship between the axis of evil and the question of initial conditions for the Big Bang. In standard cosmology, the initial conditions of the universe, the specific pattern of quantum fluctuations from which all structure grew, are treated as random, drawn from a probability distribution defined by the theory of inflation. The specific realization we observe is just one of many possible realizations, and there is no deeper physical explanation for why the fluctuations are exactly as they are. They are just random noise from the quantum vacuum. But some cosmologists have argued that this acceptance of randomness is intellectually unsatisfying, and that a better theory of cosmology should predict, or at least prefer, specific initial conditions. This is related to the problem of initial conditions in cosmology, sometimes called the problem of the arrow of time or the problem of the low-entropy initial state. If the axis of evil is a real feature of the universe's initial conditions, it suggests that those conditions were not as random as inflation predicts. They had a structure, a preferred direction, that was set by some physical process we don't yet understand. Understanding that process might require a theory that goes beyond inflation, a theory of the initial state of the universe itself. This is one of the deepest and most difficult problems in theoretical physics. It involves quantum gravity, the problem of time in physics, and the question of what, if anything, preceded or gave rise to the Big Bang. String theory and loop quantum cosmology are among the frameworks being developed to address it, and both have things to say about the possible initial conditions of the universe and whether they might be anisotropic. In loop quantum cosmology, a theory that applies the principles of loop quantum gravity to the universe as a whole, the Big Bang is replaced by a big bounce, a moment when a previous contracting universe reached a minimum size and began to expand. The contraction before the bounce is not perfectly isotropic, and the specific pattern of anisotropies in the contracting universe could potentially survive through the bounce and appear in the CMB as large-scale anomalies. This is a fascinating idea. It suggests that the axis of evil might be a memory of a previous universe, a cosmic scar from a time before the Big Bang. If the universe has been through multiple cycles of expansion and contraction, the current axis of evil might be a faint echo of the structure that existed in the previous cycle. A palimpsest of cosmic history, written in the oldest light we can observe. Of course, this idea is highly speculative. Loop quantum cosmology is not fully developed, and its predictions for the CMB have not been definitively confirmed. But it represents another thread in the rich tapestry of ideas that the axis of evil has inspired. Let me pause here and ask you something directly. Throughout this story, we have been exploring anomalies, uncertainties, and unanswered questions. We have been sitting with the discomfort of not knowing, of having data that points in different directions and theories that don't quite fit. How does that make you feel? Does the uncertainty frustrate you, or does it excite you? Do you find yourself drawn to the idea that the universe might be more complex and more mysterious than the standard model suggests? Or do you prefer the reassurance that the standard model is basically right and the anomalies will eventually be explained away? Ask yourself, what would you do if you discovered something in the data that threatened to overturn the most successful scientific model of the last century? Would you publish it, knowing that some colleagues would dismiss it as a statistical artifact? Would you hold back, not wanting to disrupt a beautiful and well-tested framework? And what does your answer say about the nature of scientific courage and intellectual honesty? These are not easy questions. And they are not questions that only professional scientists need to grapple with. In a world where evidence and data are constantly being manipulated, cherry-picked, and misrepresented, the ability to sit honestly with uncertain data, to neither dismiss it nor overclaim it, is one of the most important intellectual skills anyone can develop. The scientists who have been working on the axis of evil, on both sides of the debate, demonstrate this skill at its best. They are not advocates for a predetermined conclusion. They are investigators, following the evidence wherever it leads, honest about the limitations of their methods and the uncertainty of their conclusions. And that is one of the most important things the axis of evil story can teach us, beyond all the cosmology and physics. It teaches us what honest intellectual engagement with a hard problem looks like. Now, let's think about the axis of evil in the context of one of the most ancient human questions. Is the universe oriented? Does it have a direction? Does it have, in some sense, an up and a down? Throughout history, different cultures and civilizations have answered this question in different ways. The ancient Greeks, who developed the first systematic cosmological models, imagined a universe that was centered on Earth, with celestial spheres carrying the planets and stars around it. This geocentric universe had no preferred direction in the sense that we mean today, but it was structured, ordered, with the sublunary realm of Earth at the center and the crystalline spheres of the heavens surrounding it. Later, when Copernicus and Galileo and Newton overturned the geocentric model, the universe became an isotropic infinite space, the same in all directions. Newton's laws of physics had no preferred direction. Light travels equally fast in all directions. Gravity pulls equally in all directions. The universe became, in the mathematical sense, perfectly isotropic. Einstein's general relativity preserved this isotropy. The Friedmann-Lemaitre-Robertson-Walker metric, the solution to Einstein's equations that describes an expanding universe, is perfectly isotropic and homogeneous. It is the mathematical incarnation of the cosmological principle. But throughout this history of cosmological models, there have always been dissenters, voices that argued for a universe with more structure, more asymmetry, more preferred directions. The 19th century Austrian physicist Ernst Mach argued that the inertia of an object, its resistance to acceleration, is determined by its relationship to all the matter in the universe, rather than being an intrinsic property of the object itself. This idea, known as Mach's principle, suggests that the large-scale structure of the universe has a direct influence on local physics, which is a form of cosmological non-isotropy. Einstein was deeply influenced by Mach's principle and tried to incorporate it into general relativity, but he never fully succeeded. The connection between Mach's principle and the axis of evil is speculative, but it is interesting to note that the question of whether the universe's large-scale structure influences local physics is still unresolved, and the axis of evil might be a piece of evidence that it does. In the 21st century, Mach's principle lives on in modified theories of gravity, like scalar tensor theories and bimetric gravity, which allow for a coupling between local physics and the large-scale structure of the universe. Some of these theories can produce effects that look like large-scale CMB anomalies, and researchers have used CMB data, including the axis of evil, to constrain these theories. The full circle of the story, from Mach to Einstein to the CMB to the axis of evil, is a reminder that the great questions of physics are not separate and isolated. They are threads in a single, enormous tapestry, and pulling on one thread inevitably affects all the others. Let me now address something important about the public perception of the axis of evil and how it has sometimes been misrepresented or sensationalized in popular media. The name axis of evil is inherently dramatic, and drama attracts attention. Since the discovery was publicized, the axis of evil has been the subject of many popular science articles, videos, and podcasts. Some of these have been responsible and accurate, explaining the anomaly clearly and in context. Others have been less so, exaggerating the significance of the discovery, making it sound as if the universe has been definitively shown to have a preferred direction and that the cosmological principle is proven wrong. It is important to be clear, neither of these claims is accurate. The axis of evil is an anomaly, not a proven fact about the universe's geometry. The cosmological principle has not been shown to be wrong. It has been shown to be in tension with certain data, which is different. Tension means the data doesn't fit perfectly, which is worth investigating. It doesn't mean the principle is wrong. Similarly, some popular treatments have connected the axis of evil to pseudoscientific ideas, like the claim that the universe is geocentric and Earth is at the center of the cosmos. This is a misrepresentation. The alignment of the axis of evil with the geometry of the solar system does not mean Earth is the center of the universe. The alignment might be a systematic error, or it might reflect some large-scale physical effect that we don't yet understand. It does not mean Copernicus was wrong. Science communication matters, and the axis of evil is a case where getting the science right is especially important, because the topic touches on deep human anxieties about our place in the cosmos and on sensitive interfaces between science and religion. Honest, accurate communication about what we know and don't know is the antidote to both sensationalism and pseudoscience. This story is a perfect example of a topic where the truth, properly told, is actually more interesting and more profound than any exaggeration. The genuine mystery of the axis of evil, the real uncertainty and the real significance of the anomaly, is more compelling than any inflated claim about what it proves. The universe keeps its secrets carefully, and the process of trying to wrest those secrets from it is the greatest intellectual adventure in human history. Now, let's think about what the axis of evil means for the concept of the observable universe and our ability to understand the cosmos beyond what we can directly observe. The observable universe is a sphere centered on Earth with a radius of about 46 billion light-years. This is the region from which light has had time to reach us since the Big Bang. Beyond this boundary, there is presumably more universe, more galaxies, more matter, possibly extending to infinity. We cannot see what lies beyond the observable universe because its light has not had time to reach us. The CMB represents the edge of the observable universe in time, the farthest point from which light has ever reached us. The patterns we see in the CMB reflect the large-scale structure of the universe on scales comparable to the size of the observable universe. The quadrupole and octupole anomalies are patterns at angular scales so large that they correspond to features hundreds of billions or even trillions of light-years in size, scales that are comparable to or larger than the observable universe. This creates a profound philosophical problem. The universe we observe is finite. We cannot see beyond it. And the largest features in the CMB are features at the scale of that finite observable universe. If the universe as a whole is much larger than the observable universe, if it extends vastly beyond what we can see, then the large-scale patterns we observe in the CMB are not representative of the full universe. They are a tiny sample of a much larger reality. In this context, the axis of evil might just be a feature of our particular corner of the universe, a pattern that exists in the large-scale structure of the cosmos within our observable horizon but is not representative of the universe as a whole. If the universe is truly infinite, or even just much larger than the observable universe, then the large-scale anomalies we see in the CMB might be perfectly normal features of the universe on the scale of our observable patch, even if they are statistically unusual compared to the predictions of the standard model at that scale. This is a fascinating and slightly vertiginous idea. It suggests that what we call the universe is actually just a tiny, finite bubble in something much larger, and the anomalies we see in our bubble might be features of the boundary conditions of that bubble, rather than properties of the universe as a whole. If inflation is correct and the universe inflated enormously, the universe is probably much larger than the observable universe, perhaps incomprehensibly larger. In that case, the observable universe is an incredibly small sample of the whole. Asking whether the CMB anomalies are representative of the whole universe would be like asking whether the temperature of a teaspoon of ocean water is representative of the global ocean. Probably not. This is not a comforting thought for cosmologists who want to use the CMB to understand the universe as a whole. But it is an honest acknowledgement of the limitations of our observational situation. We are inside a finite bubble, looking out at the universe from one particular point, and some of what we see might reflect the peculiarities of our position rather than the properties of the whole. This connects to a deep philosophical problem called the problem of induction. We observe patterns in our finite sample of the universe and use them to make inferences about the whole universe. But induction is always uncertain. The patterns we observe might not be representative of the whole. The axis of evil might be the universe's way of reminding us that we should be humble about our ability to know the whole from a part. Let's now spend some time exploring the technical details of how the CMB power spectrum was measured and how the anomalies were identified, because understanding the measurement is crucial for understanding why the anomalies are taken seriously. When the WMAP satellite scanned the sky, it measured the temperature of the CMB at millions of individual points. This produced a full sky temperature map, a globe of CMB data with temperature values at every angular position. The fluctuations in this map, the hot and cold spots, represent the primordial density fluctuations that eventually grew into the large-scale structure of the universe. To analyze this map, cosmologists use the formalism of spherical harmonics. The temperature fluctuation at any point on the sky can be written as a sum of spherical harmonic functions, each labeled by two integers L and M. The coefficient of each harmonic, called A_M, describes how much of that particular pattern is present in the CMB map. From these coefficients, you can compute the power spectrum C_L, which is the average of the squared magnitudes of the A_M coefficients for each value of L. The power spectrum tells you how much temperature variation there is at each angular scale. A high value of C_L means there is a lot of variation at the angular scale corresponding to L. A low value means little variation. The standard cosmological model predicts a specific shape for this power spectrum, and WMAP and Planck have measured it with extraordinary precision. For most values of L, from about L equals 10 to L equals 2000, the measured power spectrum agrees beautifully with the standard model predictions. The acoustic peaks, predicted by the theory of sound waves in the early universe plasma, are precisely where the theory says they should be. The heights of the peaks tell us the composition of the universe, and they agree with independent measurements from supernovae and galaxy surveys. This is one of the greatest triumphs of modern cosmology. But at L equals 2, the quadrupole, the measured power is about 10 to 40% lower than the standard model predicts, depending on the analysis. This deficit is not catastrophic. It doesn't destroy the overall picture, but it is statistically unusual. And the orientation of the L equals 2 and L equals 3 patterns as we have discussed, is aligned in a way that is not predicted by the standard model. What makes the anomaly particularly compelling is that it is seen in both the WMAP and Planck datasets, which use different instruments, different frequencies, different systematic effects, and different foreground subtraction methods. If the anomaly were caused by a systematic error in one experiment, it is very unlikely that the same systematic error would appear in a completely different experiment. The fact that both experiments see the same anomaly in the same direction on the sky is strong evidence that it is a real feature of the CMB, not an artifact of any particular instrument. The Planck collaboration, which analyzed its data with extraordinary care and rigor, confirmed the existence of the low quadrupole and the alignment anomaly in their 2013 papers, their 2015 papers, and their final data release papers in 2019 and 2020. Each time, the anomaly was there. Each time, the Planck team noted its existence and its tension with the standard model, and each time, they were careful not to overclaim its significance. This pattern of careful, repeated confirmation over many years, by independent experiments, analyzed by different groups using different methods, is what gives the axis of evil its staying power. It is not a flash in the pan. It is a persistent, stubborn feature of the CMB data that has survived a decade of scrutiny. Now, let me tell you about something that happened at the intersection of the axis of evil and politics, because the story has a delightful and ironic twist. When Kate Land and João Maguejo named their discovery the axis of evil in 2005, they were deliberately borrowing the phrase from President George W. Bush's 2002 State of the Union address, where he used the phrase axis of evil to describe Iraq, Iran, and North Korea. The borrowing was a joke, a playful provocation, a way of signaling the threat the anomaly posed to the standard model. It was also excellent science communication, because the name was so memorable and so vivid that it stuck. But the irony is that the axis of evil, in its cosmological sense, is far more significant and far more mysterious than any geopolitical axis. The geopolitical axis of evil was a political label applied to specific nations for specific historical reasons. The cosmological axis of evil is a feature of the universe itself, a pattern written into the oldest light in the cosmos. And the question of what it means is far more profound than anything that played out in early 21st century geopolitics. Land and Maguejo were aware of this irony and used it deliberately to draw attention to their finding. It is a reminder that science communication is not just about accuracy. It is also about engagement, about finding ways to connect technical discoveries with the human experiences and cultural references that make them memorable and meaningful. The name axis of evil accomplished exactly that. It made a subtle statistical anomaly in CMB data into a cultural moment, a topic of conversation in coffee shops and on science blogs and in popular articles around the world. And that conversation, that public engagement with the puzzle of the CMB anomaly, has been part of what has kept the topic alive and in the public eye for nearly 2 decades. Let's now explore a question that often comes up in discussions of the axis of evil but is rarely answered clearly. What would it take to confirm that the axis of evil is real and not a statistical fluke? This is a question of scientific methodology, and the answer is more complex than it might seem. In science, we never prove that something is real with absolute certainty. We can only show that it is consistent with a very high level of statistical confidence, and that alternative explanations are unable to account for it. For the axis of evil, confirmation would require several things. First, the anomaly would need to be seen in independent datasets that are not contaminated by any of the systematic effects that have been proposed as explanations. The Planck dataset has already provided one such independent confirmation, but additional independent measurements, particularly from future CMB satellites, would add confidence. Second, the anomaly would need to be seen in independent physical probes of the universe that are not subject to the same limitations as CMB temperature measurements. The CMB polarization data is one such probe, and future satellites like Lightbird could provide it. Large-scale galaxy surveys are another, and the Euclid satellite and the Rubin Observatory will provide data on the galaxy distribution that can be used to search for anisotropy. Third, a theoretical explanation would be needed, not just a post hoc description of the anomaly, But a predictive model that says the anomaly should be there, points in this direction, has this amplitude, and makes additional predictions that can be tested. Without a theoretical framework, the anomaly remains a curiosity rather than a discovery. Fourth, the look elsewhere problem would need to be addressed. Ideally, the specific anomaly should have been predicted before it was observed, or at least the statistical analysis should be done in a way that fully accounts for the fact that many different anomalies were tested simultaneously. None of these conditions has been fully met for the axis of evil. This is why it remains a contested anomaly rather than a confirmed discovery. But all of these conditions are, in principle, achievable with future experiments and future theoretical work. And that is what keeps the scientific community engaged. The confirmation of the axis of evil, if it comes, will be one of the most significant events in the history of cosmology. It will require a complete revision of our cosmological framework, new models of inflation or pre-inflationary physics, a rethinking of the cosmological principle, and potentially a deeper connection between cosmology and fundamental physics. It will be the beginning of a new era of cosmological understanding. And if the axis of evil is eventually explained away, if future data shows it was a statistical fluke or a systematic error, that too will be a significant result. It will be a confirmation that the standard cosmological model is correct at the largest scales, and that the cosmological principle holds. It will give us greater confidence in the framework of modern cosmology and in the precision of our measurements. Either outcome will advance our understanding of the universe. That is the nature of science. Every question answered, whether the answer is yes or no, leaves us wiser than before. Now let's talk about one final, extraordinary possibility, one that takes the axis of evil and places it in the most ambitious theoretical context imaginable. What if the axis of evil is evidence not just for physics beyond the standard cosmological model, but for a fundamental revision of our understanding of space and time? General relativity, Einstein's theory of gravity, has been fantastically successful. It predicts the bending of light by gravity, the advance of Mercury's perihelion, the existence of black holes, the expansion of the universe, and gravitational waves. All of these predictions have been confirmed by observation. General relativity is one of the most precisely tested theories in the history of science. But general relativity is not complete. It has singularities, points where the mathematics breaks down and physical quantities become infinite. It is incompatible with quantum mechanics at the smallest scales. And some cosmologists have argued that it may not be the correct theory of gravity at the very largest scales either. Modified theories of gravity, like F-R, gravity, scalar tensor theories, and massive gravity, have been proposed as alternatives or generalizations of general relativity. Some of these theories naturally produce departures from the cosmological principle at large scales, including large-scale anisotropies that could look like the axis of evil. If the axis of evil is evidence for a modified theory of gravity, the implications would be stunning. General relativity would need to be replaced or modified, cosmological models would need to be rebuilt from scratch, and many of the predictions that have been so beautifully confirmed by CMB and galaxy survey data would need to be re-evaluated. This is an extraordinary claim, and it would require extraordinary evidence. But the axis of evil, as part of a broader collection of large-scale CMB anomalies, is at least consistent with the idea that something is off with the standard framework at the largest scales. It is a clue, and clues, however faint, deserve to be followed. The history of physics is full of clues that turned out to be revolutionary. The blackbody radiation spectrum that Planck couldn't explain with classical physics led to quantum mechanics. The constant speed of light that confounded attempts to detect the ether led to special relativity. The anomalous orbit of Mercury that Newton's gravity couldn't account for led to general relativity. Each of these anomalies seemed, at the time, like a small discrepancy in an otherwise successful theory. Each one turned out to be a window into a completely new level of physical understanding. The axis of evil might be another such clue, or it might not. But given the history of physics, it would be foolish to dismiss it without serious investigation. And that investigation, that serious, rigorous, open-minded engagement with a puzzling anomaly, is exactly what the world's cosmologists are engaged in right now. So let's arrive at the present moment and take stock of where we are. The axis of evil was discovered in CMB data from the WMAP satellite in the early 2000s. It has been confirmed by the Planck satellite, the most precise CMB experiment ever conducted. It remains unexplained by the standard cosmological model. Numerous theoretical explanations have been proposed, ranging from systematic errors to exotic new physics, but none has been confirmed. Future experiments, including LIGHTBIRD, Simon's Observatory, CMB, S4, Euclid, and the Rubin Observatory, are expected to provide new data that will either confirm or challenge the anomaly. The axis of evil is not just an astronomical curiosity. It is a challenge to the cosmological principle, the foundation of modern cosmology. It is a test of inflation, the most successful theory of the early universe. It is a potential window into the topology of the universe, the nature of dark energy, the existence of the multiverse, and the physics of the pre-inflationary epoch. It is one of the most important and unresolved questions in science today. And it is a reminder that the universe is under no obligation to be simple, symmetric, or easy to understand. It is vast and old and complex beyond our current comprehension, and the signals it sends to us, carried in the oldest light we can observe, are not always easy to interpret. The axis of evil is one of those signals, sitting in the CMB data like a question mark written in ancient light, waiting for an answer. You should ask yourself, as you go about your day, what it means to live in a universe that might have a direction. What it means to look up at the night sky and know that embedded in the faint glow of the microwave background, too cold and too subtle for any human eye to see, there is a pattern that aligns with the plane of the solar system, with the direction of the ecliptic, with a cosmic axis that no model fully explains. What it means to know that the oldest light in the universe carries a secret that humanity, for all its brilliance and ingenuity, has not yet deciphered. The universe is speaking. We built the instruments to hear it. Now we need to understand what it is saying. And that understanding, when it comes, will not just be a scientific discovery. It will be a moment in the story of consciousness itself. A moment when minds that evolved on a tiny planet around an ordinary star in an unremarkable galaxy figured out something profound about the nature of the reality in which they are embedded. It will be a moment worthy of the universe. But we are not there yet. The mystery remains. The axis of evil continues to stare back at us from the oldest light in the cosmos, patient and silent and deeply strange. And somewhere in a laboratory or an observatory or a university office, a scientist is looking at the data right now, running a simulation, checking a calculation, arguing with a colleague, trying to understand. Trying to answer the question that the universe has posed to us in the language of microwaves and statistical anomalies and ancient photons. That scientist might be the one who finally cracks it. Or the answer might come from somewhere unexpected, from a theorist who hasn't yet considered the problem, from a connection to another field that nobody has thought to make, from a new experiment that reveals something completely surprising about the CMB. Science works that way. The greatest discoveries often come from the least expected directions. The history of cosmology is a history of surprise, of predictions that missed and anomalies that turned into paradigm shifts. The axis of evil is waiting for its moment. And when that moment comes, it will be one of the greatest stories ever told. The CMB is not just data. It is a letter from the beginning of time, written in the language of light and heat and the quantum fluctuations of the void. We have been reading that letter carefully for decades, and most of it makes beautiful, elegant sense. But there is a passage, a strange and stubborn passage, that resists our interpretation. A passage that points in a specific direction across the sky, that aligns with the plane of our solar system, that seems to say something about the nature of the universe that our best theories cannot fully capture. That passage is the axis of evil. And until we understand it, until we know whether it is a cosmic message or a cosmic illusion, the universe will keep its deepest secret. Close your eyes for a moment and imagine it. The universe is 14 billion years old. It is vast beyond comprehension, home to hundreds of billions of galaxies, each containing hundreds of billions of stars, each surrounded by planets, some of them perhaps harboring life. All of this emerged from a tiny, hot, glowing plasma that expanded and cooled and organized itself into the structure we see today. And in the light of that ancient plasma, in the faint microwave glow that fills the universe in every direction, there is a pattern, a direction, an axis. Whether that axis is the first clue to a revolution in our understanding of the cosmos, or whether it is the universe's way of reminding us that statistics can deceive even the most careful minds, we do not yet know. But we are looking. We are listening. We are building bigger telescopes and more sensitive detectors and more powerful computers to help us understand what the universe is telling us. And the universe, ancient and patient and gloriously indifferent to our timelines, will eventually reveal its secret. Or perhaps it won't. Perhaps the axis of evil will remain forever at the boundary of what we can know, a reminder that the observable universe is finite, that cosmic variance limits what we can learn, and that some questions about the nature of reality are beyond our observational reach. Even that would be a profound discovery. Even acknowledging that there are things we cannot know, boundaries to human knowledge set not by our intelligence or our technology but by the structure of the universe itself, is a form of wisdom. A humbling, awe-inspiring form of wisdom. We are creatures of the cosmos, made of atoms forged in stars that were themselves born from the chaos of the Big Bang. We are the universe becoming aware of itself, turning its attention inward and outward simultaneously, asking the questions that no other known creature in the cosmos has asked. We are the universe's way of understanding itself. And the axis of evil is the universe's way of reminding us how much we still have to learn.